Okay, last one of the group. Are you ready? So I did save the special case for last. I didn't want to leave it out, you know. So in this case, let me bring out my list so we can reference it. But in this case, as we kind of start on this list and we start with the domain and we start with our vertical asymptotes, we're going to notice something a little different. So let's take our denominator, set it equal to 0. So 1 and 2, again, they go together. X squared minus x minus 2 is 0. And if we were to factor this, we would get x minus 2, x plus 1 is equal to 0, right? This tells us x is equal to 2. This tells us x is negative 1. But, I'm going to actually reference my original function. So this is our original. We've got x minus 2 over factored x minus 2, x plus 1. Do you see anything? You might notice, hopefully notice, these could cancel out, right? So we can actually think of this as 1 over x plus 1. So how does this work? So some of the math behind this shows up during calculus. It has to do with something called continuity of a function. We kind of touch on continuity, not a very proper definition, but we do kind of touch on it. So what this is going to look like, because this cancels, so because this cancels right here, this x minus 2, x is equal to 2 is what we call a hole in the graph, but not a vertical asymptote. In this case, only the x equal to negative 1 is a vertical asymptote, and this is a hole, and it's only because it cancels. I'll show you what that looks like kind of properly at the very, very end. But it's actually kind of cool because it means that we can actually get away with graphing this simplified function. We don't necessarily have to graph the original, more complicated one. You'll see we're really doing the same thing either way. Okay, so we do have those vertical asymptotes, or we have the single vertical asymptote. However, this is where domain and vertical asymptotes would disagree with each other. If this is a hole, that means that the function k of x is not defined, right, at x is equal to 2, because there's a hole there. So even though it doesn't translate to a vertical asymptote, our domain is going to disagree, and our domain is going to take both values out. So if I was to draw that, we have a hole at 2, and we have a vertical asymptote, also a circle on here, also undefined, at negative 1. And our function is defined everywhere else. In other words, if we went back to the original format and we plugged in a positive 2, we would still get 0 in the denominator. The difference is going to be at k of 2, we actually kind of go a step worse, and we actually end up with 0 in the top and in the bottom. And again, this is a calculus term, but this is an indeterminate form. So we address this, it's just not very much in this class. Okay? So we have our domain, we have our vertical asymptote, the only one, and we know where there's a hole in our function. The next thing we need to determine is a horizontal asymptote. So for our horizontal asymptote, we look at 1 over that x, right? I'm using the 1 over x plus 1. And so we look at that 1 and that x, and we notice the degree in the top is smaller, and the degree in the denominator is larger, and these are degrees, right? So that automatically means we have a horizontal asymptote at y is equal to 0. Okay, so if we were to sketch those two out, and so we're here at negative 1, we can actually draw in that vertical asymptote. And remember, we're kind of focusing on that reduced function, if you will, 1 over x plus 1. Right, and then we've got this horizontal one, but it isn't y is equal to 0. So I realize it's hard to kind of show, especially without color, only in pencil, stuff like that. So I would say at least just label that it's a horizontal asymptote so it's clear that you know that it is on your graph. So in looking at this, what else would we need? Well, we can look at the zeros of our function, also known as the x-intercept, right? Zeros of our numerator. But our numerator is a 1, right? So when we set that equal to 0, we actually encounter a false statement. So we actually drop this, so there are none, right? What about a y-intercept? Well, that's f of 0, which is 1 over 0 plus 1, 1 over 1, or 1. So there is going to be a y-intercept at the point 0, 1. So if we graphed that, 1 would be here. So we've got a point right there. Okay. The other thing I just want to jump back to right now is our original function. Our original function, x minus 2, x squared minus x minus 2. Remember we had that hole at x is equal to 2. So we actually do need to figure out what is 2 when we plug it in to this new version of the function. So as we kind of go to list out our other values, let's pick this pen right here. So we have x, f of x, and we're using 1 over x plus 1 to do this. I really should figure out what the value at 2 is. So at 2, we have 1 over 2 plus 1, which is a third, which is a pretty small point, which is fine. But 1, 2, and 1/3, this is a point. And I have to be really careful about how I draw it. This is an open point. Remember we said that this is a hole? This is the location of it. So it's a point that would agree with this function, right? This function would agree with our original x minus 2, x squared minus x minus 2. It would agree with that everywhere except this point. On this graph, it's a closed dot because this one doesn't know any better. On this graph, it's an open circle because it's a hole for it. So I want to make sure that hole is accounted for. It actually gives us some pretty good direction because I would say that our graph is something like this. And I do have to stop there and kind of pick up after it like this. What we don't know is what the function looks like on the other side of our vertical asymptote. So I would recommend plugging in some other numbers. So something like -2 maybe. So that's 1 over -2 plus 1, 1 over -1, or just -1. Go down here, that's -1. And then we go to plot -1, and then there's -2. Let me put it top so you can see it. 2. You have a point right there. Maybe -3 or -4, just for some good measure. -3 plus 1 is -1/2. So it's getting quite a bit closer. -3 right here. And if you were to plug in values between -1 and -2, maybe -3 over 2, that's where you would get some more values defined in kind of that area right there. So we end up with, hopefully a little smoother than that, but something like this. Okay? I will point out that what we ultimately ended up graphing, 1 over x plus 1, is pretty much our baseball function, right? With a shift to the left one. You can also use your topics from way long ago in chapter 2 to help you out with this material. Okay?